Yeah. Hello, guys. Welcome back to Getting Started with Security. And today is day 3. So, if you guys can just let me know in the comments if I'm audible and my screen is visible. Just an initial check. Okay. I guess there are people yet to come. Okay. So, we'll just start for. Okay. Yeah, I'm audible. Yes. Okay. Fine. Okay. I guess we can get started in like 5 minutes or so because I'll wait for people to come in. Okay, and one more announcement today is that I have shared the links that I will be using today on the Slack channel, and it is titled as Day 3 Forensics Links. Okay. Okay, let's wait a little bit. While we are waiting, if you guys have doubt from yesterday's session, you can ask. So someone is asking as to what is bit commitment, right? So bit commitment is, say you want to toss a coin over the phone call, okay? And say I toss a coin and you are you want to know what the result was, but I can actually cheat, right? As in, even if the coin was tails, like say if I say heads and you take tails, okay, I just toss a coin and the result was not in my favor, okay, but I can actually say that it was in my favor and prove you wrong. But integrity and cryptography can help you in, making sure that you do not go back on your words. I guess, yeah. The thing is, the mathematics behind it is too much, so don't get it complicated. So, okay. So what we can do is, since we finished our cryptography lessons on day 1 and day 2, we can just do a recap on what all we did. Okay. So we'll just go through stuffs that we did. Okay. Where is- give me a second, guys. 1 second. I'll just go through all the stuffs that we did on day 1 and day 2. Okay. So on day 1, we went with a brief introduction of cryptography and a little bit of history. Then we did CI triad and applications of cryptography. Then we started off with the basics structure of cryptography with encryption and decryption. I guess I'll just share you the slides and you'll be able to understand. Okay. So we started with a brief introduction of cryptography. Then we went to applications of cryptography and CIA triad. Then we started off with the process of cryptography. We did encryption and decryption. Later on we went through security through obscurity and what it is. Then the new era of cryptography was discussed. The difference between classic and modern cryptography. Okay, so from the previous 2 days, I would say the basic operations of cryptography was or is a little bit more important than the rest of the stuff. Okay, so you should know these 4 operations pretty much, like it should be like in your mind pretty much all the time. So if anyone asks you what is a XOR or shifts, you should be able to tell it. Then we went with types of encryption, symmetric and asymmetric encryption. Okay. Proceeding forward, we did a little bit of Caesar cipher, substitution cipher, and Wigner cipher. Then we proceeded with the process of cryptanalysis. We did break some of the ciphers. Okay, we broke Caesar cipher. We didn't try breaking substitution cipher because it would be, too much of effort. So that was the conclusion of day 1. For day 2, what we did was we started on with passwords, and then we did see some of the hashes, how hashes are made. I'll just share the slides for day 2. Yeah, so day 2 we started off with so I did forget to tell you what private key and public key were in the first day, so we just discussed that thing. But then we went to passwords, the hashing of process of passwords, the dictionary attacks, and how to defeat dictionary attacks using salting. Okay. We did discuss some of the properties of hash functions. Then we discussed about 2 hashes mainly, MD5 and SHA. Not discussed as in you were just introduced to 2 algorithms. Yeah, furthermore, we discussed hashing and encryption, like hashing versus encryption, how we can break hashes. We did Diffie-Hellman. We broke Diffie-Hellman. We broke Diffie-Hellman. Now, what are the limitations of Diffie-Hellman? And how to secure Diffie-Hellman using PKI, public key infrastructure, or RSA. Then we achieved confidentiality and integrity using hashing and encryption using this process. Then we did a little bit of RSA's introduction. So that concluded the cryptography for day 1 and day 2. So today we'll be starting off with forensics on day 3. Okay. So there was a doubt as to, okay, can we do one? Can you demonstrate the practicals of Linux tools and okay. What I can do is I can try to record a video of myself, as in my screen, me using the tools, and I can put it on Slack so that you guys can try it out if you want. Okay. Or else we can do it on day 7. If you guys are willing to join on day 7, we can do it there. Yeah. So let's proceed with forensics today. Okay. Now we'll go with the first thing is files. Okay. Now, file to understand file systems, you basically first need to understand the way in which files are stored, right? So that is why first we'll discuss what is Endianness, then we'll proceed forward with file format, followed by magic number, and then a little bit of EXIF data. Okay, so what is Endianness? Okay. Endianness is the order or sequence in which the data is stored. Okay. Say some people like, for example, some people just like it to be represented as it is. Some people change it and represent it. Okay. So there are two basic expression used for Endianness. It is called, okay, let me use my pointer. So they use either big Endian or little Endian to express their Endianness. Now say you have a data. Okay, now first we'll discuss what is big Endian and little Endian. So no need to go through the whole paragraph. I can just tell big Endian byte order is, you can say if you are given some data which is not represented in any format, it is just normal data with you, the raw data, that itself is in big Endian. Okay. So generally Motorola, Sun, ARM, MISP, they all use big Endian representation. Now the little Endian representation is a little weird. Okay. Basically Intel uses it. So most of the Windows system that you have of Intel, I guess they use little Endian byte orders. Now we'll see how to represent little Endian and big Endian. Okay, so given a data, so this is a data in hexadecimal because you can see there is an OX prefix to it. Okay, so the actual data is 0, 1, 2, 3, 4, 5, and 6, 7. Okay, so if you do a 32-bit representation of this, okay, and this is a 32-bit representation, right? Because is it 32-bit representation? Okay, we'll get it cleared later. Okay. So in 32-bit representation, what you do is you take 4 bytes at a time and you reverse it. Okay. So 6, 7 comes first. Okay. So give me a second here. I'm so sorry for this. I should have seen it earlier. Sorry guys for that. So big Endian is as it is. Okay. So the big Endian data representation is same as 0, 1, 2, 3, 4, 5, 6, 7. So you can see the big Endian representation here as 0, 1, 2, 3, 4, 5, and 6, 7. So when there is no change in the data, as in the raw data format, it is same as big Endian. But little Endian, what you can do is you can see the 6, 7 is represented first, then 4, 5, 2, 3, and 0, 1. Okay. So this is the little Endian. We'll move forward then. Okay. Now say we have this big of a data, and how do we represent it in a 32-bit little Endian format or big Endian format? So for big Endian, it is the same as the raw data itself. So it will be 3120 4D, all this thing. You should make sure that this is a hexadecimal representation, and that is why there are characters from A to E inside this. So A to F. So you have A, you have E. Okay, here. Now the little Endian, what you do is you do 4 bytes at a time. Okay. So until here, it is a first chunk of data. So what you do is 61 comes here first, then comes 4D, then 20, and then the 31 here. Okay. So since this is the first block of data, then you go to the next block of 4. Okay. 1, 2, 3, and 4. So you start on with 53 here, Then you represent 20 here. Then you give 6E and then 6M. And this is how the little Endian is achieved. The difference that you can see here is for the big Endian, there are no appended zeros at the last because this is the whole data. And so even if you append zero, it means it is the same, right? And since when you do it for little Endian, say it ends here as your last block. So you don't have any more data. So you actually append as many zeros as you want to make it a block of that much size. Okay? And that is why you are getting here 6 zeros followed by 7 4. Okay, we'll move forward. Okay, so file formats. So everyone would have experienced a variety number of file formats. Say there are multiple numbers of file formats. Now every file has its own functionality, its features, and sometimes it is harder to recognize a file just with the extension itself, right? I'll show you what I mean by that. Okay. So first we'll see what is a magic number or the file signature. So every file that you have, it has its own signature, and that signature helps you understand what the file is. Okay. And not the actual, what do you call it? Extension that you see on the file name is not always your uh, actual file. I'll tell you what I mean by that. Okay. So I'll share another screen. Okay. Give me a second. Okay. Now give me a second, guys. I'll just share my screen. Just asking for help with the. 1 second. Uh, Mohit, can you hear me, please? If you can accept my screen share. Mohit. Hey, Mohit. Mohit. Okay. Guys, you'll have to wait until my screen is approved for sharing. Okay, until my screen is approved for sharing, if you guys have any doubt until what I've discussed right now, you can ask me. I guess you would have a little doubt in the little Endianness format, right? Uh, Guys, give me 1 second and I'll just message people on. Yeah, so my screen is back there. Give me 1 second, guys. Okay, so what we can do is we'll go to magic number. Okay. Okay, so as you can see, this is a photo, right? And you can tell it because it is marked as JPG, right? Okay, this is an PDF, right? So if I click, now they say the PDF is corrected, right? Okay, now let's see if we can open the PNG file. Okay, this is also it looks like corrupted. Okay. The thing is, when they say this, you really don't know if this file was originally meant as PDF or was it meant as image or something else. So what we can try doing it is we can try to change the file extension. Okay. Now if we can see, we are able to see that this was actually an image which was renamed as a PDF, and that is why it wasn't being able to open. Right. So we will convert back this to PDF just to keep it there. Okay. Now this image, which it looks like a PNG image, I converted it from a PDF to PNG. As in, I didn't convert, I just renamed the extension from PDF to PNG. Now the thing is, how do I know that what kind of file it was before this? And that is where your magic number comes in to help. Okay. Okay. So to understand what magic number is, we'll have to go through the file signature once again and the hex editor. Okay. So we'll go through the hex editor right now. Okay, so this magic number is what helps you to understand if it was a PDF before and then converted to a PNG, or what kind of transformation was done between the original file to get the new file. Okay. So as you can see here, if you have the magic numbers as this, okay, you can say that it was originally meant to be a PDF. If you have a magic numbers of this in the, I'll show you where exactly to find it, you'll be able to see it. So it was meant to be an L file. If it was 5A4D, it was meant to be an EXE. Okay. Now the thing is, this what you can see here, it can be in both ways, right? It can be in big Endian as well as little Endian. So you should keep that in mind to check for both the sides. Okay. So now we'll try to do a hands-on and see where we proceed. Okay. Okay. So I did share with you guys a link for hex edit on the Slack. If you're not able to find it, you can just type hex editor on the browser and you'll be able to get there. Okay. Okay, so what we can do is now we'll try to open the file which we were trying to open as a image, but it looked like it was corrupted. Okay. So we'll try to open that thing. Okay. So GirlScript, magic number, beautiful. Yes. Okay. So when I open it here, you guys can see that the first representation here in text says it is a PDF. So as you guys can see here, it says it was a PDF. And this is the magic number for PDF. Okay. So as we just discussed today, the magic number of PDF is this, right? So that is what you are able to see it here. Okay. 25, 50, 44, 46 is your magic number for PDF. And that is the reason you can say that uh, the file that I was trying to open wasn't successful because we renamed it, like, we did not rename it correctly. Right? So we'll once again go to the tab. Okay. So here we'll try to now, rename it to PDF. Okay. And now we'll try to open this thing. So now it correctly opens, right? So that is why magic number is so important to understand what type of file it was before you made any changes to the file extension. Okay. I hope you guys got that stuff. Now we'll come back to our presentation and we'll move forward. Okay. Data is so, as we discussed, for file formats, every file there are some metadata that it stores. Okay. So as we have seen, the file signature or the magic numbers that they represented in the starting bytes of the file is a metadata of that file, right? Metadata is something, metadata is the data about the data. Okay. So every file will have its own properties and metadata. So an image file might have a metadata called EXIF data. So EXIF in short is exchangeable image file. Okay. So almost every camera, almost not everything, but every camera, digital camera that you use uses EXIF annotations. So what is EXIF annotations will look at. So EXIF can store your shutter speed, your exposure, your focal number, your metering system, date and time, and sometimes it can even store the GPS information that the image was taken at. Okay. Now we'll try to do. I've also shared the link for the site where you can look for the EXIF data on Slack. I'll tell which link exactly it is. Okay, so it is the first link that I've shared. It is renamed as it's named as EXIF. So we'll go to okay. So to understand what is EXIF data, what you have to do is you go to this website, choose a file that you want to know. Okay. Now say I want to know about this photo. Okay, upload. Okay. Now as it says here, like this whole stuff is the EXIF data. Okay. So it says it was taken from Canon. It also depicts what model it is precisely, the aperture it was taken with, the focal length, the flash, all those data are recorded here. Okay. So this is why you should be careful when you upload a photo to the internet. Okay. Because the data is already present in the file and people can know where it was taken, how it was taken. I will try this out with. So this doesn't have a GPS coordinate, right? Because not every EXIF data comes with a GPS coordinate because unless and until you enable the GPS coordinates while taking the photo, the image will not be able to store it. Okay. So we'll try with one that has a GPS coordinate. Okay. Okay, so along with this huge number of data, you can also see that there is GPS positions that it has. Okay, so you have 43 degrees north and 11 degrees east as the exact precision at which this photo was taken. Okay, you can see the date and time also at which the photo was taken. So make sure that next time you upload a photo that it does see. If you don't want people to let know of your address, and you still take a photo which allows GPS coordinates to have as an EXIF data, and then sharing that image is useless if you're not sharing the address, because anyone who knows something about EXIF data can easily get to your address. Okay, so make sure that while using every file system, you know the properties of that file and what that file actually can contain. Okay? So we'll move forward with. Okay, so that was until EXIF data. Okay. So before proceeding to steganography, if you guys have any doubt, I can take on doubts. Okay. Okay, so people did have some doubt, and okay, so someone asked, why are we taking 4 pairs of numbers at a time in Little Endianness? Okay, I'll tell you why exactly. This is a good question. So I'll go back to Endianness. Okay. Okay, we'll go to the previous one. Okay. Where's my pointer? Okay. So say this is your whole data that you want to represent in Little Endian. Okay. Since it is a hexadecimal representation of the data, every character in this representation can be represented by 4 bits, right? So 0 can be represented with 4 bits, 1 can be represented with 4 bits, 2 can be represented with 4 bits, and so does every character in a hexadecimal representation can be represented with 4 bits. Right? Now, when you take 2 bits at a time, it is actually 1 byte. So when you say 67, this is actually 1 byte of data. Okay, this is 1 byte of data. This is 1 byte of data, and this is 1 byte of data. Now that is the reason I mentioned here 32-bit representation. Okay, for 32-bit representation, what you will do is 1 byte to make it 32-bit. You need 4 such bytes, right? And that is the reason the 4th byte is represented first here. Then the 2nd byte is represented here. Then the 3rd byte is represented here, and the last byte is represented here. Same is the case for this huge chunk of data. So we'll go till 1 byte, 2nd byte, 3rd byte, and the 4th byte. Okay. Until 4th byte, this is one chunk of data. That is the reason you get 6-1 first here, and from 6-1 it is totally reversed for 32 bits. Okay. So from 6 you get it reversed till here. Now you once again start it from here, you go 32 bits here, and then you once again reverse it back. And that is how you get the Little Endianness. I hope you got that answer. Okay. Is the magic number of every PDF same? Yes. So every file, every magic number of a PDF will be same. So, okay, for an example, I can show you this. So you can go to Google and say list of signatures. and it will give you a Wikipedia link. Okay. So on the left hand side, you can see the magic numbers. Okay. So these are the magic numbers. Okay. And these are the file systems. These are the file names. Now you can see that, say for this one, you see this is represented as in some Indian, but you're not sure of it. It might be Little Indian, it might be Big Indian. Because since you do not know the actual raw data, you will not be able to tell if this is Little Indian or Big Indian. Because this might be even Little Indian or Big Indian. So they have given both the combination. So if you find both this combination, it will always be a PCAP file. So PCAP file is a packet capture file. Okay. So when you capture file from say Wireshark or such packet capturing softwares or tools, you get a file with an extension of PCAP or PCAP-NG. Now we'll see where the PDF lies. Okay. We'll go and check for, okay, we'll directly check where PDF is. Okay. Okay. So here is the PDF. So for PDF, it will always be this structure. Okay. So every PDF document will have this. Now say, I don't encourage people to do so, but say you want to hide a file in plain sight. Okay. Say you want to hide an image from your siblings or someone in the plain sight. Okay. What you can do is you can just actually change the extension of it. So if from PNG you just make it PDF and they'll not be able to open the PDF. Right? But since you know what the file can be, you can use the hex editor to know what the original magic number was, and since you know the magic number, you will be able to decode it back to the original file. Okay, fine. Now we'll go back and we'll take one more out. Yeah, so one more doubt. Where is, okay, I did it out. Okay, the magic number is for the extension. So it will be, yeah. Benefit of Little Endianness. Okay, actually there are no benefits as such for Little Endianness. It is just a way of representation. Okay, now the only benefit, as in not actually benefit, that I can think of is, since Intel is widely used, most of the systems that you see are Little Indian. Okay, so if you develop a system and if it is not compatible with Little Indianness, okay, then your system won't work on a machine that actually uses Little Indianness. Okay? And when I say Little Endianness, I'm saying it in terms of low level programming, as in if you're actually programming in say assembly language or in terms of uh, bytes. Okay, I'm not sure if many of you have done it, but you might be able to do it in your fourth year or third year of undergrad. So you might have the chance of writing an assembly code on say 8086 microprocessor or 8085 microprocessor, and I believe that uses, I'm not sure, but I believe it uses a big Indian notation. Okay, but if you try to give it a Little Indian notation and see if it works, it will not respond to you correctly as you want it to. Okay. uh, then FA downloaded images will show EXIF data or not. Okay, so the thing is, it depends upon the compression as well. So if your image is so compressed that you remove most of the EXIF data, then you'll not be able to get the EXIF data back, right? So JPEG is a type of compression. And if you use a lossy compression and you lose some EXIF data, you can actually hide the EXIF data, right? But if you can actually hide or delete an EXIF data, I'm not sure about it. But I guess there is a way to delete it, as in, okay, we can do something here. Okay. What we can do is we can go to, okay. So remind me at the end. Okay, we'll try a way to see if we can remove or hide the EXIF data from an image. Okay. So at the end of this class, please do remind me to do so. Okay. Okay. Then we have. Is there any limit for big Endianness? Okay. So I'm not sure what exactly you mean by that question, but what I think is you're asking me if there is any limitations to the big Indianness. Okay. So Indianness is just a type of representation, right? So it really doesn't affect much unless you shift it onto some machine that uses other Indianness. Okay, so now Indianness is the reason I'm talking about Indianness is because, say, for stuffs like buffer overflow, okay, which you'll be learning on the application security stuff, you should actually know what kind of Indianness the machine uses in order to exploit it. Okay. So you see, when the people say they hacked a system or an application, they were, I'm talking it in terms of binary level, okay, not a brief overview level. They knew what the endness of the system was, and only then they were able to break it. The next question was, WhatsApp download photo profile doesn't show EXIF data. Is it because of the compression? Yeah, I guess it is because of the compression that they do, or maybe they would have stripped off the EXIF data. But I guess mainly because of the compression that they do, because WhatsApp is more famous for compressing it to a lower size. If I upload, okay, a screenshot will not reveal EXIF data because to have an EXIF data, you need it to be a digit. It needs to come from a digital camera. Can we change the magic number of any file? Yes, you can change the magic number of any file, but you'll not be able to retrieve back. Say you change the magic number of PDF to something of a magic number of PNG. Okay. So the machine will think now that it is a PNG and it will try to read it as a PNG. But since other metadatas will not support PNG, that photo might get crashed. Okay. Can EXIF data be falsified as well as that of images? Yes. So if you can strip or if you can make changes to the EXIF data, it can be falsified, I guess. Yeah. Yes, I'll proceed with my slides now and then we can get back with the doubts later on the slides. Yeah, so we'll move forward with, yes. So we were there at steganography. Okay. So steganography is a practice of concealing a message file or some data within another file. Okay. So this is how, like, this is the most famous way of, concealing message in plain sight. So to understand steganography at another level, I mean, not at the basic level, but at an intermediary level, you should know how an image is formed, what pixels are, what is a bit depth. Okay. So I know people would know what in images. Pixel, I would say it is the smallest representation of an image. Okay. So you can't go beyond as in much less than a pixel in an image. And bit depth is, okay, you'll understand what a bit depth is. Okay, I'll use my pointer here. Say a black and white image. Okay, so you guys should know the difference between a black and white image and a grayscale image. Okay, excuse me, guys, 1 second here. So a black and white image is different from grayscale image in a way that black and white has just two colors, black and white. But a grayscale image has multiple shades of black and white. So the bit depth of black and white is 1 bit because you just need 1 bit to represent these two colors. Okay. For grayscale, which is one layered, okay, you need 8 bit of data, right? Sorry, yeah. So you need 8 bit of data because grayscale, since you need 8 bit of data, the maximum number of images that you can store is 2 raised to power 8, which is 256. Then, so the grayscale is called one layered or 1 bit depth image. An RGB image is called a 3 layered bit depth image, which consists of 24 bits because every layer of RGB is, say, the red layer has 8 bits of its own. Okay, not 8 bits. It needs 8 bits to represent every pixel in that one layer. Okay, so for an RGB image, you need 24-bit to represent one pixel. Okay? And since you need 24-bit, you can form 2 to the power 24 colors in an RGB image. Okay? Now, what we can do is there are basically multiple techniques to do steganography, but we'll just discuss 2 techniques. Okay? So the first technique is LSB substitution, and the next technique is bit plane modification. LSB substitution is a way to just change the least significant bit of the pixel. And since it is the least significant bit, the human eye will not be able to make the changes between the changed image and the original image. Okay. Whereas the bit plane modification, what it does is, for a given RGB image, there are 8-bit planes. Okay, because this I'm talking about a grayscale image, because a grayscale image has an 8-bit plane, whereas an RGB image will have a 24-bit plane, because 8-bit for every layer. So bit plane has 8-bit, bit plane modification uses 8-bit plane. Okay. So bit plane is, I have not gone into details here, but if you want details for bit plane modification, I can get back after the class. So we'll just proceed with the LSB substitution here. Okay. So say these are two different pictures here. So this picture and this picture, there is a difference, but the human eye is not able to understand what the difference is. Okay. I just want to ask you people to tell me if there is a way to find out if there is any hidden data in any of these two images or not through any method. As you guys can guess in the comment if there is a way to, you know, tell if there is data hidden in these images or not. What I'm saying is, one image is original without any data in it. The other one might have, may not have it. So is there a way to tell if there is some data hidden in it or not? So okay, by checking file size. No, the file size will be the same because you're just changing. It might change, it might not. Okay, someone said hex dump. Yes, hex dump is also possible, but there is an easy method to tell if these two are same or not. See, I'm talking in terms of, you know, a normal user, then a computer science user, to tell if there is a difference between two images. Okay, I guess I'll tell you the answer for this at the later slide, at the last. Okay. Now what we can do is we can try the hands-on for this image. Okay. So I did share the link for steganography as well, and it is there in, yeah, we have a Slack message where I've sent you the links called normal stego. So normal stego, if we use it, I'm not sure if it is letting me in. We'll try online steganography. So this was the one. Sorry. I'll change the links there to reflect the same. Okay. So say to encode a message in a file, you generally use any open source. So in Linux, there is a tool called OpenStego, which is more famous than these online web services. So you can use it for your own practice. So say you use this image, okay, and you say you want to hide something secret, and then you just encode it. Okay, so this secret is represented as this in the binary representation. So this is the binary representation of your message. Since this image is too huge, as in if you count the number of bits in this image, it is very much, too much. And changing just these many bits in this image will not provide a significant change in this image. That is the reason you see it as this. And even though this has a message in it, you don't see any changes between the two. Okay. And say you want to decode this message. Okay. So you go to decode and you just ask it to decode. Okay. Okay. So as you can see, what this file did here was, there's the image that we wanted in the beginning. Okay. And from there, the rest everything is garbage, right? So what this encoding and decoding of a steganography image is based on the implementation of that system, as in the steganography system. What I believe the user here might have done was change every LSB to what our message can contain, as in to change every LSB of a pixel and modify it such that it can contain our message. And to decode it back, they have checked the LSB of every single pixel, and that is why you get all these garbages. So this is trying to check the LSB of every single pixel, and it is not able to decode it back. So this is basic steganography. Now, as I said, if you guys want to know more about the bit plane modification example, you can stay much longer after the class ends. Okay. I'll get there. Any doubts? If you have doubts, do it fast, as in make it fast, or else we can have the doubt session at the end. I guess we can have the doubt session at the end because it's already time. Right? Okay, so we'll understand what an ADS is. So ADS is also a mechanism to hide stuff. It is called alternate data stream. So ADS provides, so people who are familiar with Mac, there is a feature called resource fork, which was like introduced way long back. So ADS is similar to resource for Macs, but ADS is implemented only in NTFS. Okay. So what ADS does is you can store it is same as steganography. Okay. So you can store a whole video inside a small text file. Okay. So actually it doesn't store inside the text file. What it does is it creates a separate stream within the original file and then links it to that stream. So we can see an example for that too. And ADS is using ADS you can pretty easily transfer malwares to other systems as well. But there should be a way to trigger the malware on the other system that you transfer it to. Okay. So we'll try on some ADS access. So give me a second and I'll just try to share my 1 second guys. I'll just okay. So I'll share my screen. Okay, so I guess you guys are able to see my screen. Okay. Now say you want to know how basically an ADS works. So what you do is first you create a victim file in which you want to create an alternate data stream. So I'm using command prompt here and the commands that I'll be using, I'll have the link for it in the Slack. So these are basic commands. So it's just notepad and the name of the file that you want to edit. Say you have something called as victim.txt. So say you create a file victim.txt and okay, so you're not able to see the notepad, right? So what I can do is I can just echo it. Okay. So I'll echo hello there. I'm the victim. Say victim.txt. Okay. So now victim.txt has hello there. I'm the victim. Okay. So let's see if I can tag the victim here. So is there a way to, if you guys know how to cat a file on command prompt, can you let me know? Guys, the equivalent of cat. Is it type? I guess it's type. Okay. So as you can see that the file contains hello there, I am the victim. Now what you can do is you can create another. Okay. So before going there, look at the size of the file. So the file is currently 32-bit long, 32 bytes long. Now what we can do is we can try to add something else, again, append something else again to see if the file size changes or not. So we'll see if the file contains the appended text. Yes. So it does contain the appended text. And we'll check the size once again. So as you can see, if we modify the contents of the file, there is a change in the file size of victim.txt. But now say I want to make an alternate data stream, what I do is I echo something, say I echo secret, then my password is okay into I echo my password into victim.txt. Now the thing to remember is to access an alternate data stream, what you have to do is you have to provide a colon and then the name of the stream, say hide.txt or with hide. Now, if you check the size of the directory, it is still the same as 61, but you can get back your secret key, as in your hidden data that you have stored it in the victim.txt file using the ADS string. Okay, so what you do is get back my right, victim.txt, and from there I want the hide part. So it isn't showing it here. So I guess if we try to open it via Notepad, okay. So you guys are not able to see this, but I'll share it. However. 1 second. Okay, so I just opened my Notepad here, and it displays the hidden stream that I have entered through the command prompt. Okay, so this is how you use generally basically ADS. Okay, but it is way easy to use ADS through PowerShell. So if you guys aren't familiar with PowerShell, I would suggest you to look into it. I'll share some links at the end of the class on how to get started with PowerShell. Now let's continue with our presentation for email forensics. Okay. I guess it's yeah, bear with me for like another 15 minutes, guys. This might be a little long. Okay. So email forensics is very important because you should be able to understand from where an email has come. Is it legitimate? So many people fall for the prey of phishing emails, right? So you should be able to understand if an email is legit or not. So there are multiple ways to know that. The basic way to know is to actually go through the contents of the file as an email and to try to understand if it might be legit or not. The other way is to look into the email headers of a given email. So we'll try to look into the email headers. So there are multiple sections that an email header contains. It contains the from section, which refers to the address which it originally started from. Okay? And this is the easiest to forge because from of an email can be easily forged because it is the way an email protocol is implemented. Okay? So there are services which provide you with the ability to change the from section of your email. Uh, if you guys want that link, you can personally email me on the Slack and I'll share it with you. The next thing is reply to. Okay. So reply to is a section where your reply to the email will be sent to. So you should see if the from address and the reply to address are from the same organization or not. Okay. Then there is a return path. Generally, it is the path in which it can go back to the reply to email. Okay, there is something called as message ID, which is important because as you can see, the message ID is identified by this particular string, which is made as some unique character string at the rate the site name of that particular email providing service. Okay. So if you don't know the site name of that service from which the email has come, it is highly recommended that you ignore that email. Then there is something called received. So received is basically your data. Okay. And the last, okay, so received, there are multiple received sections because an email has to reach from one place to another, and in that process it does by going through multiple stations. Okay, so every recipient in the way will have this received section. So say if an email takes 10 people to reach you, as in 10 email recipient hosts to reach you, so there will be 10 received sections in the email. So it is better to go through all these email headers and to understand if there is anything that makes it look fake or not. Okay. Yeah. I guess we can cover the malware forensics for tomorrow. I guess, yeah. So malware forensics, I haven't kept much as such because malware forensics, I was not able to find open source malware that I can ask you to examine. If possible, we can do it on the later stages of this outreach class. Okay. So I guess I'll wrap up this class here for today, and I'll take the doubts section now. Yeah. So if you guys have any doubts, you can proceed forward. Ah, yeah. So I'll just stop the share, and we can. Guys, doubts if you have. So I'll go through the doubts. Okay. Uh, yeah, and I guess I did ask you to remind me of something, right? I'm not sure. Yeah. There is a doubt. Can EXIF data be falsified as well as data? We did this. Okay. How do we see/know the Endianness of the machine we want to exploit? So there should be a way for you to, in generally, if you know the operating system of a machine, it is pretty easy to determine what kind of Endianness it uses. Because most of the manufacturers don't change the Endianness frequently, so that if they change it frequently, it makes their products unstable and not compatible with each other's, right? So they try to keep the Endianness of every system that they manufacture either big Endian or little Endian. But most of the time, it will be little Endian. Okay. Ryan, if you can ask your question of then change the magic data to previous one, isn't it possible? If you can rephrase that question, it would be great. The next thing was, okay, so I was going to tell you the difference as in a method to tell if these two images are different or not, right? So the way to tell if these two images are different or not is calculating the image difference of this. Okay. I'll try to see if I can calculate image difference. So we'll see if we can calculate image differences or not. Yes, we can. Okay, so what we'll do is we'll go to Steganography. We'll create a file here saying get my password. Okay, encode it. Here is your image, right? Yes. So we'll give this image here and we'll give an image of the original. Okay, okay, here is it. Okay, so as you can see here, if you calculate the image difference of an image with the hidden message and the message without the, I mean, the original image, if you can see some disturbances, it means there is some data in it. Or it might be the case that the image has been modified while transmission or at storage. Okay. It is not necessary that the image is, what do you call, image contains the secret, but it is for sure that it has been modified. One more way to know if the image is changed or not from the classes that we learned from the past 2 days. Any answer? Any method to know if two images are same or not from the classes or the topics that we learned from the past 2 days? Okay. Try to get the answer for that, and I'll clear the doubts until then. Okay. Oracle. Okay. Okay, Linux tool for steganography. One tool that I can think of right now is OpenStego, and OpenStego is pretty common in Linux. I'm not. Yes, I guess you'll be able to find it in Linux. Yes, you can use OpenStego. And steganography, there are multiple ways of implementing it. So there is one way without providing a key to the steganography implementation, and another is, one is keyed steganography and one is non-keyed steganography. So you can implement steganography in both the ways. But how that message is being stored? Okay, so message is being stored. So in steganography, you try to change something and such that the changes in a given pixel is not too much that the human eye can differentiate from the original and the new one. Okay, you can just replace the whole image with your data, but that will make the humans understand that there is something changed between the two images, right? So you should be careful enough to change the image in such a way that a pixel is not changed, say, by more than 20% or so. Okay, yes. So hashing and substitution is a way to check if the two images are same or not. You got that right. Okay. Uh, so some people do have doubts about CEH and how to prepare for the exam. So if you guys have doubt, I can provide you a Zoom link and we can have a conference, video conference there. So let's keep this just to the like just to getting started with cybersecurity. Okay. Any more doubts, guys? Okay, so this is a good question. So without the original image, to be used for image differentiation, how can we know if the image file has some secret message added to it? I would say that would be pretty difficult. Yes. So, what I believe is if you directly try to decode a message, there are possibilities. Say, you can try implementations of all common implementations of steganography and try to get the data if the file contains data. Else, there is no way for you to understand if there is data or not. I guess so. Or maybe there might be some, you know, advent of technology in terms of AI and machine learning, where they are able to understand if there is some changes in an image or not. I'm not sure, but it might be possible. Okay, how do I go about forensic of a physical acquisition full device capture? How do we proceed if the device has full device encryption? Once you've acquired the physical drive, okay, I mean the device, and if it is totally encrypted, the first thing that you need to make is to make a copy of that device. Okay. Once you have the copy, do not meddle with the original one. Always try to break the copy you have. Okay. So that is how they generally proceed forward. Because the original physical acquisition that you have made is considered as an evidence. Okay, so you do not ever tamper with the evidence. You make a copy of it and then you try to break it. I guess. I guess if you have any doubt, yeah. Any more doubts, or should I wrap it up? I guess I'll wrap it up for today, and we can discuss. We can discuss malware forensics. So malware forensics, you'll have very less hands-on. It is pretty much theoretical. Okay. If needed, I can share the slides because it is all theoretical, and I'll just share the slides. And tomorrow we can continue with. Okay, so we'll see tomorrow. I guess tomorrow we'll be starting with web security. I'm not sure. Hold on, guys, for a minute. Yeah, tomorrow and day after tomorrow we'll be going with web security. I guess that would be pretty interesting than forensics, what we did today. Yeah. So I'll wrap it up. If you guys have any doubt, do ask me on Slack. I have a great night, guys. Thank you.